So today we're going to talk about how to find the distance from a point to a line in 3 space. So one way to do this we've already talked about a few sections ago was to use projections to calculate the distance from point to the line. But as we're going to see today, you can also make use of the cross product when you know the vector function of a line. So let's start with a vector-defined function, rt equal to p0 plus td, where t is allowed to range from negative to positive infinity. So that's going to be our parameterization for L. So p0, recall, will be on line L, and d is the direction vector that is parallel to L. And so q is our point on the line L that is closest to the point P. Alright, so P is off of the line and Q is on the line. And perhaps if we see a picture of that, that'll be more explanatory. So here is the point P0 on the line. Here's the direction vector for this line L. And here's the point P that is off the line. And so it's point P that we're trying to find the distance from. So from P to Q, that perpendicular distance, we defined Q to be that point on the line that was actually closest to P. So we're going to try to find this distance. So the formula that allows us to do this is right here. It is the magnitude of the cross product of D and the vector created from P0 to P divided by the magnitude of the direction vector. So I'm going to show you where this formula comes from. It comes from using just simple trigonometry together with a theorem from a few sections ago. So again, notice that point P is not on the line, and line L is parameterized by this generic vector value function p0 plus t times d. And so this expression I'm saying is going to give us the distance from that point to the line. So the trigonometry part of it, if we go back to that original triangular diagram I had a few minutes ago, this is the trigonometry piece of it. As a right triangle, we can say that the sine of theta is equal to the length of the opposite side divided by the length of the hypotenuse. So the length of the opposite side should be the magnitude of the vector PQ, and the length of the hypotenuse should be the magnitude of the vector P0P. So sine of theta should equal the magnitude of this side divided by the magnitude of that side. Therefore, the magnitude of this side should be equal to the magnitude of this side times sine of theta, and that's what we have written right here. So that's the trigonometry piece. And then from a few sections ago, we had that the magnitude of u crossed with v is equal to the magnitude of u times the magnitude of v times the sine of theta. And so for the vector u, I'm going to say that's the direction vector, and the vector v, I'm using p0 to p. So this is u, magnitude of u cross v equals magnitude of u times magnitude of v times sine of theta. If you compare these two expressions, you see they have a lot in common. See the magnitude of p0p times sine theta and the magnitude of p0p times sine theta are both present here. So if I solve this second equation for the magnitude of p0p times sine theta, by dividing both sides by the magnitude of d, I will have two different expressions for the magnitude of p0p sine theta. And since both of those expressions are equal to p0p times sine theta, then they must also be equal to each other, and that's how we can say that the magnitude of the vector pq is equal to the magnitude of the cross product of the direction vector and the vector p0p divided by the magnitude of the vector d. And the magnitude of the vector pq is this distance that we're trying to find, the distance from the point P, not on the line, to the line L at the point Q, which is closest to P. Okay, so let's do an example of this. Find the distance from the point P, -630, to the line L, determined by the points Q and R defined as given there. So P is off the line and Q and R are both on the line. So we can use Q and R to get a vector equation for the line by first using Q and R to produce a direction vector and then also allowing either one of these points to be P0. So if we just arbitrarily pick Q to be the point P0, then that point would correspond to R of 0 when the direction vector for L is given by D, defined as you see here, 1, 6, -7. So where did the 1, 6, -7 come from? That comes from taking R and Q and subtracting associated components. So 4 minus 3 gives us the 1, 5 minus a -1 gives us the 6, and -2 take away 5 gives us the -7. So we have the direction vector and we have P0. If I'm going to find the distance, I'm looking for the magnitude of PQ, where P is the point off the line. I can now find this magnitude, the magnitude of the direction vector, and if I define P0P, I can then cross D with P0P and find its magnitude and get the desired distance. So we have the direction vector, we might as well go ahead and find its magnitude. Square 1, square 6, square 7, add them all up, take the square root, and get the square root of 86. And we also formed that other necessary vector P0P by subtracting associated coordinates. And make sure you do subtract in the proper direction here. Finding the direction vector, it actually didn't matter which direction you subtracted, but doing P0 to P is going to matter. So that is -6 minus 3, 3 minus -1, and 0 minus 5, and that's where we get -9 for -5. So now that we have vector D and vector P0P, we can cross them with the purposes of finding the magnitude of that cross product. So to cross D and P0P, I'm going to take the determinant of the matrix where ijk is in the first row, the components of D are in the second row, and the components of P0P are in the third row. And if we do that cross product properly, we should arrive at the vector -2, 68, 58, using the cofactor expansion. Okay, so once we have that vector, we can then find its magnitude by squaring each of the components, adding them together, and then this is simplifying, and I get 6 times the square root of 222. So the last piece of the puzzle is to simply put the values in the proper space in the equation. So we had that the magnitude of PQ, which is the distance we desire, is equal to the magnitude of this cross product that we just found, 6 times the square root of 222, divided by the magnitude of the direction vector, which we found earlier, the square root of 86. And reduce and simplify, and we get 6 times the square root of 111 over the square root of 43. And that's the rest of the material in section 10.5. So next time we will pick up with section 10.6, which is material dealing with the equations of planes and distances with planes.